Let's look at a few more examples of solving trigonometric equations. Here we have the equation sine squared x is equal to 3 cosine squared x. Now in this problem, things are a little bit more complicated because we have two different types of trigonometric equations. Here on the left-hand side, I have a sine squared x. On the right-hand side, I have a cosine squared x. Sometimes it can be possible to use our fundamental identities to rewrite our trig equation. In this case, if we divide both sides by cosine squared x, that leaves us with sine squared x divided by cosine squared x is equal to 3. Now, the combination of sine squared x divided by cosine squared x can be rewritten using our quotient identity for tangent. This is tangent squared x is equal to 3, and now we have our equation written in terms of a single trigonometric function. From here, we can now begin to isolate our trig function tangent of x. And to do so, we would have to take the square root of both sides. Taking the square root of tangent squared x gives me tangent of x, and taking the square root of the right-hand side gives me root 3. Now, remember, whenever we take the square root of a variable, which we are doing in this case, we have a variable inside of our tangent function, we have to recall that there are both positive and negative roots that we have to include. So we get the tangent of x is equal to plus or minus the square root of 3. Now that we have our trig function isolated, we can go to our unit circle to identify the locations of our solutions that have a tangent value of root 3 or negative root 3. Well, to find tangent of an angle, we take the y-coordinate and divide by an x-coordinate, and that combination has to give me a root 3 or a negative root 3. That means my y-coordinate must have a root 3 on top, and notice that dividing by a half is the same as multiplying by 2. All right, therefore, all of the ordered pairs with a 1/2 and a root 3 over 2 will end up being solutions. We have one here at pi over 3. The tangent of pi over 3 is root 3. We have another solution here at 2 pi over 3. The tangent of 2 pi over 3 would be negative root 3. We have another solution down here at 4 pi over 3. The tangent of 4 pi over 3 would be positive root 3. And here at 5 pi over 3, we have another solution, right? The tangent of 5 pi over 3 would be negative root 3. So those are all of my solutions on the interval 0 to 2 pi. But we must recall that there are an infinite number of solutions to this equation. There are an infinite number of angles that have positive or negative root 3 as a tangent value. So let's think about the most compact and simplified way to write that expression. Let's take a look at these two angles here, pi over 3 and 4 pi over 3. Notice that they are actually pi radians apart. So anytime I start at pi over 3 and add or subtract a multiple of pi, I am going to end up at another solution. So, to account for all the angles that terminate in either of these locations, I can say x is equal to pi over 3 plus n times pi. Notice we have n times 1 pi in this case because that is going to bring us to either of these two locations. The same thing can be said for 2 pi over 3 and 5 pi over 3. Notice that they are exactly pi radians apart. And to accommodate for all angles that terminate in either of these two locations, we can say x is equal to 2 pi over 3 plus n times pi. All right, there we have our general solution. These two answers account for all of our possible solutions to our trigonometric equation. Let's see another one. Cotangent x times cosine squared x is equal to 2 cotangent x. Again, this is a challenging problem because we have two different types of trig functions. I've got cotangents and I have cosines. Well, notice that there are two terms that have a cotangent x associated with them. That means that it is a common term. If it's common between two terms, then we can factor it out. Well, before we factor, what do we need to do? Set the equation equal to 0. One thing to make sure of, avoid the temptation to divide out trigonometric functions. Notice you might think, oh, I can divide the right-hand side of the equation by cotangent of x, divide the left-hand side of the equation by cotangent of x. This will get cotangent of x and cotangent of x to divide out. Don't do this, okay? Canceling out trig functions will create problems. You will lose solutions when you do that. Do not divide out trig functions. Notice that in the last problem, we were able to divide by a trig function because it didn't cancel anything out. It just allowed us to rewrite the expression, right? Nothing canceled out. We just rewrote the expression. That's okay. On the other hand, don't divide out trig functions. So instead, we want to group all these terms on one side of the equation and then factor. So here we have cotangent x times cosine squared x minus 2 cotangent x is equal to 0. Now we can see that cotangent x is going to be a common factor between these two terms. We can factor this into cotangent x times cosine squared x minus 2. And just like you do with your algebraic equations, we can now set each one of these factors equal to 0, because the zero product property says if either one of these quantities, either one of these factors equals 0, the equation will be true. That gives us cotangent x is equal to 0, and cosine squared x minus 2 is equal to 0. Now, this factor still leaves us with a little bit of work to do. We can add 2 to both sides of the equation and take a square root, leaving us with cosine of x is equal to plus or minus root 2. Remember, always include plus or minus when we are taking square roots of terms with variables. Okay, now that we have our trig functions isolated here, cotangent x equals 0 and cosine x equals plus or minus root 2, we can go to our unit circle. Let's identify the locations where cotangent is equal to 0. What angles have a cotangent of 0? Well, cotangent is derived by taking the x-coordinate and dividing by the y-coordinate. If x over y equals 0, that means that the x-coordinate must be 0, giving us angles of pi over 2 and 3 pi over 2. Now, what about this one here? Cosine x is equal to plus or minus root 2. Well, that's actually impossible. This is not going to give us any solution here. There are no angles that have a cosine value of positive or negative root 2. If you think about this, the unit circle, it's called the 1 unit circle because the radius is 1 unit. Our greatest value of cosine is 1. Our smallest value of cosine is going to be negative 1. Root 2 is greater than 1, and negative root 2 is less than negative 1. So this is not going to give us any answers. So these are our only two solutions between 0 and 2 pi. How can we write our general solution now to account for all of our possible answers? Well, notice that pi over 2 and 3 pi over 2 are exactly pi radians apart. That means anytime I start with an angle pi over 2 and add a multiple of pi, I will come back to another solution. That gives us x is equal to pi over 2 plus n pi. And as we already said, cosine of x equals plus or minus root 2. That's not possible. It can't happen. Therefore, this factor does not give us any other solution. Key takeaway from this problem: do not divide out trig functions. You will lose solutions. Do not divide out trig functions. Instead, set the equation equal to 0 and factor out your greatest common factor. Let's look at another one here. Solve the following trigonometric equation. We have 2 sine squared x is equal to 2 minus the cosine of x. Well, again, challenges arise because we have two different types of trig functions. I've got a sine squared x and I have a cosine x here. All right, sine x and cosine, two different types of trig functions. That being said, we need to think, is it possible to rewrite the expression in terms of a single trigonometric function? Well, we have a sine squared here, and thinking to our Pythagorean identities, we know that sine squared x plus cosine squared x is equal to 1, which means that sine squared x is equal to 1 minus cosine squared x. Again, we can rearrange those identities, right, in a variety of different ways, meaning I can replace this entire quantity, sine squared x, with 1 minus cosine squared x. That leaves me with 2 times the quantity, 1 minus cosine squared x, is equal to 2 minus cosine x. Well, why did that help me out? Now, the only trig function that I have in my equation is cosine of x. So let's continue to do some algebra. Let's distribute here. This 2 is connected by multiplication. We can distribute the 2 through. That gives me 2 minus 2 cosine squared x is equal to 2 minus the cosine of x. Notice that if I subtract 2 from both sides of the equation, these 2's cancel out. And now I've got negative 2 cosine squared x minus a cosine of x. Well, this is actually in the form of a quadratic. What we want to do is set it equal to 0 and factor. So let's add 2 cosine squared x to both sides. That leaves me with 0 is equal to 2 cosine squared x minus cosine x. And now we can factor out our greatest common factor of cosine x. 0 is equal to cosine x times 2 cosine x minus 1. And setting each of these factors equal to 0 and isolating our trig function gives us cosine x is equal to 0, and the next factor gives us cosine x is equal to 1/2. Now that we have these trig functions isolated, we go to our unit circle. Let's identify all the angles that have a cosine value of 0. Well, cosine corresponds to the x-coordinate. Our x-coordinate is 0 here at pi over 2 and at 3 pi over 2. Then we can identify the angles that have a cosine value of 1/2. Which ones have an x-coordinate of 1/2? Well, that's pi over 3 and 5 pi over 3. So these are all of my solutions on the interval 0 to 2 pi. However, we need to account for all of our possible solutions. Remember, there are going to be an infinite number of solutions to this equation. Well, make note here that our angles pi over 2 and 3 pi over 2 are exactly pi radians apart. So anytime I add a multiple of pi to pi over 2, I'm going to come to another solution. That means I have x is equal to pi over 2 plus n times pi. Now, there is no real relationship between pi over 3 and 5 pi over 3, any multiple that will get me to either of those two locations. So we just have to write our answer for each of these locations separately. If I add 2 pi, or a multiple of 2 pi, to pi over 3, I come back to another solution. X is equal to pi over 3 plus n2 pi. And if I add a multiple of 2 pi to 5 pi over 3, I come back to another solution. Therefore, we get x is equal to 5 pi over 3 plus n2 pi. And so there is our general solution to this trigonometric equation.